Alright, and here is case 3 for project 3. We're going to be doing viscous turbulent flow now. Geometry and mesh are the same as before, so we'll go straight into the setup. Double precision for me, 4 processors. Alright, first thing we're going to do is swap our model from viscous SSTK Omega to Spalart Almaris. I think that's how you pronounce it, I'm not sure. Okay, before we swapped our residuals to a lower value so that it would get more accurate, we're not going to do that here because this turbulent flow has a very hard time, it seems, getting below 10 to the negative 6 for convergence. So we're going to leave it at 10 to the negative 3, and we're going to swap our fluid values for some that play a bit nicer for turbulent flow. Just going to have a density of 1, a viscosity of 10 to the negative 5, and we're going to go to our boundary conditions, inlet, and change our velocity to 10. Now this velocity of 10, if you do the math, gives you a Reynolds number of 1 million, which exceeds the 500,000 critical Reynolds number, so this is turbulent. Now we're going to swap the bottom and top walls to symmetry. And so that way we get a bit of variation, or sorry, not a bit of variation. That way we get a bit of, I don't know what the hell I'm saying. I'm going to cut this out. Alright, and the wall, make sure this is no slip, and stationary. Stationary, no slip. Great. Okay, reference values. Compute these from the inlet. Great, it updated. And not going to change the methods at all, going to go straight to initialization, and more settings, 25 iterations, initialize. Okay, and now click into calculation, 200 iterations, calculate. Alright, our calculation is complete. Let's take a look at the residuals. It really struggled to just get below 10 to the negative 3. Like it plateaued here. And if you try to let it go further, it just refuses to. So I just swapped my residuals to 10 to the negative 3. Maybe a better mesh would help in some way, but I'm not sure. Okay, so plots. Let's see our velocity variation and our pressure coefficient. We'll do the pressure coefficient first. Look at that. Pretty good. Starts at 1. Goes down and rebounds quite nicely and is basically flat. It does a little, it comes up a little bit here at the end, but this is pretty much perfect. And also we can look at the velocity variation, which I don't know if I showed this in the laminar video, but it's about the same as it is here. It's just flat 0. It's, of course, because you have no slip conditions. All right, and now reports. Forces, and let's just print our cylinder forces. Alright, pressure coefficient is 0.42, viscous is 0.01, so it basically is negligible in comparison, and the total is 0.43. Okay, and now we can go to our results and get our contours and streamlines in. Okay, first one we're going to do is the velocity contour. Whatever, doesn't matter what the name is. Symmetry 1, we're going to do velocity, and 301 contours, apply. Alright, here's our velocity contour. Looks very similar to laminar, but there are some differences that you can pick up on. So, of course, stagnation point here, high pressure at the top and bottom, and a wake region. But if you compare this side by side, you'll notice with the laminar before, you started to see separation, not separation. You started to see the flow depart from the cylinder at about this point, before the halfway point. Now it seems to do it just after the halfway point, so it stays on for a bit longer, which is, of course, what is expected in turbulent flow. And this results in a narrower wake region that restores quicker, it looks like. I was hoping to see some more distinct features, but this seems to work. There is some velocity going on in here. It's not just dark all the way, which is also good. That tells me that there's some sort of maybe eddies or turbulence going on in this region. And maybe we'll see some streamlines go towards it, but I doubt it. We can start from the inlet and do 1,000 points. And here we go. Okay, yeah. So it's basically the same as laminar flow, except the differences I already mentioned. A much narrower wake region, and it converges and looks basically normal. Like, you couldn't even tell if this is before or after the cylinder. So yeah, I was hoping once again that I could see some sort of swirling in here, but I just couldn't make that work for any reason. For some reason, I mean. But now we'll do the pressure contour, and that will be the last thing we need to do. We'll do 501 and location symmetry 1. Alright, and so here is our pressure contour. As you can see, high pressure here, medium to low-ish pressure here, but generally speaking, it's not that far off of the steady state pressure. And right here is the lowest point of pressure, and that's when flow separates or flow breaks off of the cylinder right here. So that's totally what I expected. All right, that was case 3, and that was project 3. Thank you.